All right, how's it going, Sister Johns? We're just here to talk about all of our group problems, and so I think we're going to go through each question and each teach a question, 1 through 4 at least, and then we're going to do number 5 together, like you asked us to. So I guess I'll start on number 1. So for number 1, I got, so what are the 3 chemical components of a nucleotide? So you have your phosphate groups, right? Your pentose sugar, and your nitrogenous base.
Yep.
Yeah. Did you get that?
Yeah.
Mm-hmm. Okay, and then so for the carbons, as far as attached to the sugar or whatever in the DNA or RNA, the 1' carbon is adjacent to the ring oxygen and is attached to a nitrogenous base.
That's what I put.
Okay. And then, so what you got?
Yeah, I got this.
And 2' carbon is attached to 2 hydrogen atoms in DNA and attached to a hydroxyl group and hydrogen atom in RNA.
Yeah, I got the same.
Okay. And then the 3' carbon is important in DNA RNA synthesis and is also attached to hydroxyl group. What you guys got?
Yeah. Pretty close.
So, did you get anything for the 4' carbon? Because that was really...
I didn't find anything about 4'.
Yeah.
I couldn't find anything either.
Yeah, I just put no function.
Yeah, I couldn't find
Yeah, it's just kind of there. I even tried to Google to find some answers because I didn't see anything in the notes, but nobody knows what the 4th carbon is.
Yeah, I don't know either. I watched some of those videos too, and I couldn't find anything. Okay, I guess we'll just move on from that one. So the 5' carbon is attached to the phosphate group and is also important in DNA and RNA synthesis.
Yes.
Yeah.
Okay. Number 2. So what are the 4 nucleotides that can be used for RNA synthesis? Please write the entire name of the chemical. So you got guanosine, adenosine, uridine, and cytidine, right?
Yeah.
Wait, isn't it guanine? Guanine and adenine, uracil and cytosine, or is it the nucleoside?
It's a nucleotide. I can't remember. That's a good question.
Well, let's look that up. Because I have the scenes as well, but maybe...
So a nucleotide is a base attached to a sugar and one of the 3 phosphate groups. If a guanine is attached to a ribose in a single phosphate group, the nucleotide is guanosine monophosphate.
So it's guanosine, adenosine,
uridine, and cytidine.
Okay.
So the nucleosides. Wait a second. It's asking for the nucleotides.
The 4 nucleotides.
So the nucleotide would be guanosine monophosphate, right? Correct?
What was it saying in the notes about that?
So it says a nucleotide is a base attached to a sugar and 1 to 3 phosphate groups. If guanine is attached to a ribose in a single phosphate group, the nucleotide is guanosine monophosphate. If guanine is attached to deoxyribose in 2 phosphate groups, it's called deoxy. So that must be. Is that referring to? Is that referring to DNA, or?
So nucleotide is going to have a phosphate group, a pentose, and a nitrogenous base, right? But I think with this question, it doesn't really mention how many phosphates.
Yeah.
So it's just talking about the nucleotides, right? So even there, there's an example for the nucleotide of guanine. And it says the nucleotide is guanosine monophosphate. If the guanine is attached to deoxyribose with 2 phosphate groups, it's called deoxyguanosine.
So ribose is RNA, right?
So
it's going to be the monophosphate.
yeah.
So it's what is it again? So guanosine monophosphate.
It could be used for RNA synthesis. So guanosine monophosphate.
And then,
So that's what it's asking for, right?
I think so.
That's the one that it's not a deoxy.
Well, it asks for specifically for a nucleotide, and the nucleotide by its definition in the note says is a base attached to a sugar in 1 to 3 phosphate groups.
So we don't have to put how many phosphate groups on there, right? We just need to put
Well-
the guanosine. Because it could be attached to monophosphate,
Oh, that's true.
diphosphate.
Yeah, so as long as we put
That's true.
guanosine, because we don't know how many phosphate groups.
Right. So there, it would have
So
been...
it is guanosine, adenosine, uridine, and cytidine, right?
Yeah, I think so.
Okay, and then DNA is deoxyguanosine, deoxyadenosine, deoxythymidine, deoxycytidine, right?
That's what I put.
had to.
Okay. Then for C, suppose the genome of a newly discovered species of bacteria contains a double-stranded DNA molecule composed of 24% thymine, percentages of the guanine, cytosine, uracil, and adenine. So thymine pairs with adenine, so it's also going to be 24%. And then you find the other 2%, like the rest of the percentage is what is that? So it's 52%. So you divide that by 2. You're going to have 26% guanine, 26% cytosine, right?
Yeah.
And then 0% uracil because it's DNA.
Exactly.
Okay. Suppose the genome of a newly discovered species of virus contains a nucleic acid composed of 38% adenine, 27% guanine, 35% cytosine, and 7% uracil. What can you conclude about the genetic material of this virus? So, I mean, all I could come up with, and I don't know if you guys came up with anything else, is that it's made up of RNA because it has uracil in it.
Yeah.
Yeah.
Is there anything we can conclude about it? I know it said something in the notes about, or I feel like maybe it was one of the videos. It talks about like if it has more guanosine and cytosine in it, then it's like stronger or something like that. I can't remember.
I mean, it would make sense if it's got different percentages because it's not like they don't have pairs, right? Because I mean, if it's just a single strand, then it doesn't matter what the percentage is. I would think.
Okay. Right. Okay, so I'm going to do number 3.
Yeah, so number 3 was kind of confusing the first time I went through it. But I think I figured it out. So to find the length of the DNA portion of the mouse chromosome 1, it says it's got 197 million base pairs. And so you multiply that number by the 0.34 nanometers of each base pair, and then that gives you the length in nanometers, and then you multiply that, you convert that to meters, and I got 0.06698 meters. Yeah.
So you do like each base pair is separated by 0.34 nanometers. Okay.
Right. So it's like...
Yeah, so you got 0.067, or I guess it's...
Yeah, I mean, I just had like 5 digits. Alright, so, and that one's different than the rest of them. For B, this is based on what we learned in class, but... so I did my best with the notes that we had, and I think I figured out how to do that one too, because we're trying to condense the DNA into a chromosome eventually. And so to make it smaller, to fit inside the nucleus and all that, you have to condense it with nucleosomes and histones and whatever. And in the notes it said there was like, I think, 146 to 147 base pairs that go around every nucleosome. And then between each of those, there's like 50 base pairs that it says there, the average length of the linker. So I think you just add those two numbers together, 146 and 50, or 147 and 50.
Yeah.
And then you divide the 197 million base pairs by that number, and it should give you how many nucleosomes you have. So if you did 146, like I did, I got about 1,005,102 nucleosomes. But if you did
147, you get 1 million.
Right. So, I mean, it's almost the same number because we're talking about millions, but... and then for C, it changes to the human genome, and that's got a lot more base pairs. It's got about 3 billion. And so to figure out how many histones you have to first find the number of nucleosomes like you did in the mouse one and B. But then divide that number, or multiply that number by how many histones there are within each nucleosome. So doing the same kind of method, dividing 3 billion by 50 plus 146 or 147, I got 15,306,123 nucleosomes, which are then converted to 1,224,489,800 histones.
Is that because you multiplied it by
Yeah.
50?
For which one?
So-
I divided the 3
Yeah.
billion by
The
50 plus 146,
Yeah. Mhm.
and that gave me the number of nucleosomes.
Mhm.
And then you
and then you
multiply
just translated
that.
that to histones.
Right. So you multiply that by 8, because there's
By
8 histones
Okay.
in each
Gotcha.
nucleosome.
Well, I guess I was confused on that. Like, so why is there 8 if there's 4? Like, I
So
am confused about
I
that.
wasn't sure about that. So there's like 4 different pairs of histones. I
Okay.
guess would make more sense. So there's like 4 groups, but each group has 2 histones in it, and that kind of is how we get D, because D is asking how many histone H3 are predicted to be found in the nucleus. And so if you can find the number of histones, that's how many there are total. And then if you divide that by 4, that should give you the number. That should give you the number of histone H3s, because there's 2 in each one.
Okay.
So yeah, pretty sure that's how we did that one.
Okay.
Okay.
And then D.
Moving on to number 4 now.
I think we got one more on this last one. D.
For D?
Yeah.
So that was the one that I just said, like.
Oh, okay,
Because
sorry.
we're finding the histone H3s, and so yeah, you just divide the number of histones, that 1
You got like
million
30
number.
million.
You divide that by 4, and that should give you the number of H3s.
You got like 30 million or whatever.
Yeah, 30 million, like 600,000.
Alright.
Roughly.
Okay. Yeah, sounds good. So for number 4, it was pretty simple, I thought. So for part A, it says which molecules above are nitrogenous bases, and that would just be guanine and thymine.
What about uracil?
I have uracil as well.
Well, was uracil? Oh, I didn't see uracil on the list. I just saw uridine. Yeah, uracil also would be one of them then. And then for B, which molecules above contain ribose, I put guanine, uracil, guanosine, uridine, adenosine, adenosine triphosphate, and I guess thymine would also be one of them. So all of them that don't have deoxy in it.
Well, I think the ones that are just nitrogenous bases, I don't think those ones have ribose on them yet.
Yeah.
That's
So-
true. So
So
I
it's
just have 4.
So adenosine, uridine.
guanosine, adenosine
Guanosine
triphosphate.
So 4,
Yeah,
Right.
those are the ones that I have.
because those are the only ones associated with RNA, right? And ribose is RNA.
Right.
Okay, and then for nucleosides, so I put adenosine, uridine, guanosine, and actually, I think it might just be those 3. Or is deoxythymidine?
Isn't
I
thymine one
put
of
that
those?
one on there too.
Okay, because I have it there, but
Isn't so deoxythymine, thymidine, and then thymine as well, right?
is thymine a nucleoside?
Thymine is just a nitrogenous base, isn't it?
That's what I thought, yeah.
Yeah, I'm confused between nitrogenous bases and nucleosides.
So a nucleoside is just like the base and the sugar group, right? Or is it like a base?
So it says a nucleoside is a base attached to a sugar.
Yeah, and so nucleotide is the base with the sugar and the phosphate group.
Right.
And so the nitrogenous base would just be like the thymine, but since it's attached to a sugar, it's it would be like deoxythymidine.
Right.
Okay.
Okay, and then for D, which molecules above are nucleotides, I put deoxyuridine diphosphate, deoxycysteine monophosphate, and adenosine triphosphate.
Yeah, that's what I got too. So all the ones that have phosphate groups on them.
Mm-hmm. Yep.
Sweet.
Number 5.
Okay.
Okay.
So number 5.
Suppose. Oh, are you?
Sorry. guess I don't know if we have to like calculate
For this one.
Yeah, okay.
Okay, so describe what is. Oh, suppose a DNA strand has the following sequence. Yada yada yada. Describe what is meant by the 5' on the left-hand side of the molecule.
So I was just thinking that I wasn't sure how you wanted us to answer that one. Is it that on the 5' end is where it starts reading it for DNA, for transcription, or for replication, I guess? It starts reading from the 5' and it goes to 3'.
Yeah.
Like that's
I
where
mean,
the
yeah, I think
transcription will
so.
start.
So you can predict the strand.
That's where transcription starts.
Yeah.
Okay.
And there's a free 5-phosphate. Yeah.
Starts for the RNA molecule, right?
Yeah.
For the DNA.
Doesn't it? It transcribes the RNA first, right? I guess I don't know if we even learned that yet.
Yeah, I think it's just for DNA right now. But if we are doing transcription, then it would start at the 5' end.
This is meant for the 3' end of the right. Okay, the left hand side, the right hand side. So this is where transcription ends.
I guess where they start adding in the other bases or base pairs, I guess.
What do you mean?
I think so.
Don't you add to the 3' end?
It starts at the 5' and it works its way towards the 3'. It's always the end of it, isn't it?
Sure. Like,
Let me look at it.
I'm just not sure how we're supposed to word this.
what does it say about it in the notes?
Okay. So, 2 strands of DNA are antiparallel. One strand starts with the free 5' phosphate group at the top and ends with 3' hydroxyl group at the bottom. The other runs opposite direction. The free 5' phosphate is at the bottom end. The free 3' hydroxyl group is at the top. You can predict the sequence of one strand of DNA if you know the sequence of the other strand. If one DNA strand is 5', yada yada yada, 3', then the opposite strand is the opposite. That's all it says. I wonder if the PowerPoint says anything.
So something that we didn't mention before was that on the 5' end, that's where the phosphate group is, and on the 3' end is where the hydroxyl group is.
Oh, that's true. So
phosphate groups.
transcription process begins at the 5', where the phosphate group is located. And then transcription process works towards the 3' end, where the hydroxyl group is.
Mm-hmm. That's what I'm thinking.
Do you guys have the PowerPoint? My PowerPoint isn't pulling up.
I have the PowerPoint on here, but do you think the video will end if I switch?
Here, I'll try to open it up again.
I have the PowerPoint. It's not in the same format, but which one were you wanting to
Go
look
down
at?
to like where it comes up.
This one? Or?
No, like the black ones. It's not it. Keep going. Keep going. Almost. Oh, it doesn't even get.
That's the last one.
Never mind. I guess that's the best we could do with that, right?
Yeah. I don't think there's too much more that we know.
Yeah.
Okay, so C was a sequence of complementary DNA strand that would have the capacity to form hydrogen with the sequence above.
I guess it'd be start with a 3'.
So
It does.
This one's got the double helix on it. Okay, so
It's really helpful, actually.
so the 5' end to 3' end, 3', 5', phosphate, hydroxyl. Key features. 2 strands of DNA form a right-handed double helix. The bases and opposite strands hydrogen bond according to that rule. The 2 strands are anti-parallel with regard to their 5 to 3 prime directionality. There are 10 nucleotides in each strand to complete through 60 turn of helix.
Yeah, it doesn't say anything about it.
So,
I think that's as good as we can get it.
alright.
Okay, so the sequence, that's going to start with the 3 prime, right?
Yes. Then you just put the complementary pair, right? So
So it'd be T,
wouldn't it? Oh yeah, wouldn't it be?
G.
Wait,
This is DNA, right?
yeah.
So DNA is the same. We don't have to change any of them to like use or anything like that?
No, not for this.
Okay.
No, so it'd be
So when you're starting it, do you start reading from the right also? Would it be 3 prime A T C
No,
G?
so they I'm pretty sure they should just be bonded like straight across.
yeah. So the 3 prime's right here, over here,
Mhm.
right,
Oh,
and then
so-
it goes A T T A.
Got it. Okay. All right.
So we just like write it backwards.
So
kind of.
T
Mhm.
A C.
C G.
We have a losing spot. G
C
T
Oh.
G G
C
C A
A
T
T
T
T T T A A G C C G A A T G C
T A.
5 prime.
I know I'm gonna mess that up at some point. Good thing I'm not making DNA.
Okay.
Well,
Good one.
okay, so suppose the molecule from part C is able to form hydrogen bonds with the sequence above. How many turns of the DNA double helix would be found in this molecule?
So
So
in
each
the
turn
notes-
is like 3.4 nanometers or whatever.
Well, I
Well,
think
it takes 10 base pairs for it to make a complete turn.
right.
Oh,
And so if you count there, well, there's more than 10.
4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 18, 19, 20, 21, 22, 23, 24, 25.
So it would make
Still
2.5
like
turns.
2.5 turns.
Yeah. I think.
That seems good to me.
Well,
Well,
Well, looks like we got it
is
all.
there anything else you guys want to chat about?
No, I'm good.
I'm pretty good. I think that's like the whole assignment. So
All right. Well, I know it wasn't 30 minutes, but we got through everything. So there you go. Thanks, Sister Johns.